The dominant AI paradigm from 2020 to 2025 relied on a single brute force scaling law: build massive neural networks and passively ingest static textual data to form representations of the world. This approach is hitting a rigid wall. We are seeing the limits of passive architecture. When these models are placed in novel, zero-shot environments where they cannot rely on memorized training data, their abstract reasoning performance flatlines. Anthropic's Claude Opus 4.8 provides the definitive proof of this ceiling. They recently ran the model through ArcAGI-3, a benchmark designed to test a system's ability to discover rules in unknown environments without prior instructions. This chart compares those ArcAGI-3 scores. On the surface, Opus 4.8 dominates the leaderboard, scoring nearly 4 times higher than GPT 5.5. But the absolute score reveals the breakdown in logic. The model achieved just 1.5%, leaving a staggering gap from the human baseline. Autoregressive text prediction, regardless of parameter size, appears insufficient for true abstract problem solving. Richard Sutton, a pioneer of reinforcement learning, identified the source of this failure. He argues that relying on static internal neural maps to represent reality is an architectural dead end. Sutton's central thesis is that the world is its own best model. A static neural network trained in a vacuum can never accurately map an open, dynamic, and infinite physical reality. This critique is driving a transition toward a framework known as inactive cognition. In June 2026, we are seeing the first major industrial prototypes and research papers that move away from passive representation in favor of this inactive approach. Models built on this framework generate intelligence through continuous physical and digital interaction, using their own lived experience as the primary training signal. The classic pathway is strictly linear: ingest data, build a map, output an action. The inactive pathway is a circular loop of action and perception. Static neural maps break down under unpredictable variables, while the circular loop continuously adjusts. This core adaptability relies on action-perception inseparability. To function in reality, an agent must grasp how its own movements alter its incoming sensory data. Shifting a mechanical arm changes the perspective of the visual sensor. Interacting with an object changes the light and shadow. This requirement is driving the shift toward embodied robotics, where the model can test these physical consequences directly. Perception emerges from movement. The agent generates a continuous feedback loop of physical consequences by navigating its environment. We are already seeing this inactive theory engineered at an industrial scale. The Shanghai Chuangji Institute recently released Tau0WM, a 5 billion parameter robotic world model built on this framework. This table details the scale of the model's pre-training. It ingested 27,300 hours of video, splitting its data pool between strict robotic teleoperation and unstructured first-person human interactions. Mixing datasets creates a paradox. Mapping organic human muscle movements onto rigid mechanical joints corrupts control systems. Researchers use modality-specific supervision masks to resolve this. The mask filters human video for objective physical variables, like fluid dynamics, while blocking kinematic joint angle data. This isolates physical dynamics from the human footage, ensuring all actual motor control learning comes strictly from the teleoperation data. The model extracts universal physical laws from passive observation without compromising its inactive control logic. Historically, robots used end-to-end reactive policies. A camera sees an object, and the network instantly triggers a motor. That approach is inadequate for complex, long-horizon tasks where early mistakes cause compounding failures. Test-time computation replaces the reactive policy with a 3-stage simulation cycle: propose, evaluate, and revise. First, the video action model proposes multiple branching paths of potential actions. Then, a consistency score ranks these imagined paths, identifying the single most reliable movement strategy. Finally, an action-conditioned video simulator generates a multi-angle video of the imagined future to verify the outcome before physical execution. By burning massive amounts of computational power before moving a joint, the robot probes a latent future to avoid failure in the real world. Simulating thousands of multi-agent decision trees creates a massive scheduling bottleneck. Traditional GPU clusters often struggle with this level of concurrency. This schematic details Intel's hardware response, the Xeon 6 Plus architecture, codenamed Clearwater Forest. It utilizes 3D chiplet stacking, placing 12 compute tiles over 3 base tiles to expose a dense grid of 288 efficiency cores. Those 288 cores are specifically engineered to handle hundreds of thousands of concurrent, fragmented inference loops, rather than monolithic calculations. NVIDIA and Marvell have identified a similar constraint at the network layer. Because these inactive loops distribute tasks across millions of processors, the physical interconnect network is the ultimate rate limiter for decentralized workloads. Optimizing for brute force matrix multiplication is no longer the sole priority. Modern hardware focuses on ultra-high-density concurrency, tied together by extreme network bandwidth. This architecture has erased the barrier between physical robotics and digital software engineering. On the left, a robotic model outputs joint torque. On the right, a digital agent outputs code. The cognitive loops driving them are identical. Digital agents like Alibaba's QN 3.7 Plus use this trajectory-based loop to visually read an operating system, executing commands and autonomously coding complex software over an 11-hour span. Security infrastructure is adapting directly to this convergence. Frameworks like BraveGuard are training defenses entirely on the long-term execution trajectories left behind by agents navigating a system. Whether a model is navigating a kitchen or a macOS desktop, the underlying cognitive architecture, action, trajectory feedback, and revision is now the same. These distribution curves summarize the shift defining the 2026 landscape. Computational expenditure is migrating out of the pre-training phase and into the execution phase. Intelligence now scales directly alongside how much test-time computation a model is permitted to burn to verify its own logic. The technology is moving away from a passive oracle reciting static knowledge. It has become an inactive entity generating intelligence through active trial and error.